Welcome to Institute Innovation Council event. Today we have with us Ms. Pratiksha and she will be delivering session on achieving problem solution fit digital image processing for magnetic resonance imaging. Pratiksha was born and raised in Bidar, Karnataka, where she completed her schooling and pre-university education. She pursued a degree in Electronics and Communication Engineering at Dayananda Sagar College of Engineering, Bengaluru. Currently, she works as an image processing engineer at Voxel Grids Innovation Private Limited, an India-based company specializing in magnetic resonance imaging, that is MRI technology. I welcome Pratiksha. I request Pratiksha now to proceed with her presentation.
Thank you, sir. Thank you for your warm welcome. Hello, everyone. Good afternoon. I'm audible to you, people. Okay,
Yeah,
fine.
go ahead.
I'm Pratiksha. I'm Pratiksha from Oxalgrids. Oxalgrids is an India's first MRI-based startup company. So yes, I'm like today I want to talk about digital image processing in MRI basically. So have you ever seen or undergone an MRI scan? Hello, people. Guys, I'm audible to you, people.
Yeah, you are audible, but your PPT is gone.
Yes, sir. I just want to interact with the students, so it's better for me to. Okay, fine. I'll continue. So yes, I guess everyone saw okay, no one is responding, so I'll just assume like you people saw MRI machine. Okay, today I will walk you through how MRI works, how we acquire images, and how digital image processing plays a major role in converting signal to medical images. So yes, uh, so everyone knows that our body contains 70% of water. So in MRI, the key atom is hydrogen. So water has a hydrogen. Hydrogen, like in MRI, we need hydrogen. Hydrogen protons, why only hydrogen? Because we know it's an in our body it has 70% of water, and hydrogen has proton behave that in hydrogen we have one hydrogen proton that behave like a tiny magnet due to their nuclear spin. So in normal situation, when our body is without magnetic field, that time hydrogen atom will spin randomly, in our body. So that time the net magnetic field is zero. When we say, when we place patient body inside the magnetic field, then that hydrogen protons rotation will align, like not only rotation, yeah, that will align to the magnetic field of the magnet. So, basically, MRI is an medical resonance imaging. So, in that, basically, our magnetic field of our company magnet is 1.5 Tesla. If we place patient body inside the MRI machine, then that hydrogen proton will align with the magnetic field of the magnet. So, as you people see here, it's around, if we assume the magnetic field is this direction, some hydrogen protons are aligning parallel or anti-parallel to the magnetic field of magnetic field of magnet. So yeah, after placing that, we emit an radio frequency waves. At that time, uh, like at that time that if you see this green color at protons, like whatever that is an net magnetization, that time, when we play a radio frequency onto our body, that time, so stop that after certain, when we stop that, then those hydrogen protons will come back to their initial position. That time that will emit and radio waves that will receive. We have so many receiver coils. That time we receive the radio frequency, and that we store in an case-based domain. Like after digitalization and everything, we store that as an in case-based domain. That's nothing but frequency domain. Here, like another one thing is there, that is Larmor frequency. Larmor frequency is the frequency at which hydrogen protons will spin in the direction of magnetic field. So hydrogen protons, this gamma is here. If you people see, Larmor frequency is F is equal to gamma into B naught. Our B naught is static magnetic field. That is, in our company we use 1.5 Tesla. But basically there are so many different types of magnets are there. Like 1.5 Tesla, 3 Tesla, 6 Tesla. Like yeah, if we increase the, as you see, Larmor frequency is directly proportional to B naught. When we increase the static magnetic field, that time frequency will also increase. So here in hydrogen atom, that gamma is 42.78 and B naught is 1.5 Tesla, and that overall frequency will be 63.78. At that frequency, that when we play a radio waves, that time only that the hydrogen atom will flip. So like Larmor frequency plays a very vital role in imaging. When we now we saw the like how we get image in MRI. So we store, like we don't get an image, we store those radio frequencies in after digitalization in a case space. So there are different types of acquisitions are there. Basically, traditional method is Cartesian trajectory method. In there, we have two types. Those are fully sampled case space and undersampled case space. Fully sampled case space means we collect data by line. Basically, if you see here, like we are collecting data line by line. And if we go to the undersampled case space, here we collect data alternatively. So what will happen? Why we are collecting alternatively? If a patient is inside the MRI scanner, to reduce the scan time, we are collecting data alternative lines. So yes, this is traditional method. Here we need a lot of time to collect the data. But if we follow the fully sampled case space, then that reconstruction of image will be like easier for us. Directly, like we do FFT and then we construct an image. I guess you people heard about Fourier transform? Yes. Okay, fine. If we collect the data alternatively, what will happen here? If we see here, there are artifacts are there because of these collecting of data alternatively. Okay, so like I have to get these cleared image. So what I'll do, I will there are so many different types of image reconstruction methods are there. So it involves image processing and computer vision, machine learning. So so many things will comes into the picture. I want this picture. So from this artifact to this one, like to construct that, we'll get so many reconstructions. Like this one we called as a parallel imaging. To like so many different varieties are there in that. Like in our company we use parallel imaging. And another like this is most significant one. But here like lot of neural networks, deep learning, everything will should be there, because here in non-Cartesian trajectories means like if you see here, we are collecting this case space line by line. Here alternative lines, but here we collect case space in a non-linear manner. I mean spiral or radial, whatever. Or so why we collect like that? Because this will, like, if we collect data in non-Cartesian trajectory, so that scan is like so quick. So for that purpose, we are collecting data in non-Cartesian trajectories. But here, like, we can't do here. We did direct fast Fourier transform, but here we can't do fast Fourier transform because the data is not in a linear way. It's in non-linear way. So we do NUFFT. NFT. After that also we'll get like these artifacts and like so many. If you see here, these are called as Gibbs ringing, and this ghosting. Everything will come. So to solve that, we have time variant functions. So that is based on deep learning. Like where do we need deep learning and all? Like if I do like same thing, like last month only I worked on this. Like for particular one slice, this, if I do mathematical computations, then it was taking around 11 minutes. That's not good for us. Like one patient is staying in a magnet for that long is not good for us. So to reduce that time, we use deep learning modules and all. So after using